Hey there, in this video we are talking about logical operators in C++ or other programming languages. And this covers sections 4.8 to 4.12 in the Gaddis textbook. So what are logical operators? Now, first of all, when you see the word logic, that always means dealing with things that are true or false. Logic is things that are true or false. So that should put you on alert for what you're about to see. What is true or false in programming? Well, those are Boolean expressions, right? So we use a Boolean expression as a trigger in an if-else statement to determine which path to take, which of two decisions to take. And so far, we've just been using one single Boolean expression, probably a relational operator, probably, to make that decision. But you can combine Booleans together in more complicated ways using these logical operators. So logical operators are symbols that connect multiple Boolean expressions together to create compound decisions. Now, again, these are logical operators. These are not arithmetic operators like plus, minus, times, divide. Those things take numbers and produce other numbers, right? These are not relational operators that take two numbers and produce a Boolean. Logical operators connect two Booleans and produce another Boolean, is what we have here. So there are three basic logic operators that you're going to see here. I'm listing them in order of precedence. This is an order of operations table in addition to other things. Okay, so three basic logic operators that we're interested in. And you should be familiar with them from English. They work the exact same way they do in an English sentence. So hopefully you can leverage that knowledge. There's the not operator. In C++, we use the exclamation mark for that. And what that does is that actually is just a modifier on one single Boolean. And if the Boolean was true, now this expression is false. If it was false, now it's true. So basically not flips the logic value, the truth or falseness of the original variable or expression. Then there's and. In C++, you use the double ampersand symbol for that. And an and statement is connecting two expressions, and it's going to be true if both of the connected expressions are true. Otherwise, and comes back as false. Okay, and then there's the or operator, which in C++ is the double pipe symbol. Now, on a keyboard, you look directly above the enter key. You have to hit shift and then the key right above enter, and you get this straight up and down symbol, which we call the pipe. So you have to use a double pipe symbol for or, and an or expression is true if at least one, if either one of the things you're connecting is true. So if you have the first one true, you're good. If the second one is true, or is true. If they're both true, that's good as well. Okay, so to make a long story short, not flips one truth value and needs two things to be true, and or needs just one thing to be true, at least one thing to be true. And these are really important. I mean, here we are seeing them in a computing programming context, but these exact same operators are really essential in mathematics and science and philosophy and law and electrical engineering and a whole bunch of other stuff. Some people could look at this and say, this is actually really the essential stuff that you're going to build computing and everything else out of if you dig into it in a deeper level. So very important to know your logical operators well. But they basically just work the same as the English words do. So here's a quiz slide where we're going to review that. And on this slide, you're going to see three variables pop up in some different expressions. So let's assume that the x variable is holding 12, that y is holding 5, and z is holding -4. And here are some possible logical expressions using and or not. Stuff like this. So you notice that for most of them, you're connecting two Boolean expressions. And in this case, I've used mostly relational operators for the simple stuff. The one at the end, right? The one at the end there is not, that only modifies one single expression. So let's think about that first one. The expression on the left is x greater than y is 12 greater than 5. That's true. Okay. The expression on the right is y greater than z is 5 greater than -4. That's also true. The operator in the middle, that's and, right? I have true and true. Both of those things are true. So the and expression comes back as true. Okay, so maybe pause the video like we normally do and see if you can write down the answers to the other 4. And when you're ready, restart the video and we'll see if we agree on the results. Ready? Think you got it? So the next one, the left-hand expression is true and the right-hand expression is false, right? -4 greater than 5, that's actually false. So what you're looking at here is true and false. Remember, and requires both of them to be true. So in this case, the and comes back as false. Okay, now the next 2 are ors, right? With ors, you only need at least one to be true. So in the third one, the expression on the left is 12 lesser than or equal to -4. Well, that's false. And the expression on the right is y equal to z. Is 5 the same as -4? That's also false. So I'm looking at false or false. And of course, the whole point to or is you need at least one to be true. We do not have that. So this comes back as false. The fourth one here, okay, the left-hand expression, we just said that is false. The one on the right is 5 not equal to -4. That is true. 5 is different than -4. So I've got false or true, and that's going to come back as true because or needs at least one, right? Wants one to be true, and that's what we have here. Now this last one might be the trickiest, but you can probably see what's happening. So inside parentheses gets checked first. Is 12 greater than or equal to -4? That is true. And then the not happens to it. And notice that you write the not in front of the expression that you're trying to modify. So if this initial thing was true, not flips it to false. Now, you might want to write down that last example. That last syntax comes up in the next lab, and people generally find that a little bit tricky the first time they see that, but not only affects one thing, it affects what's right after it. And remember, the not is way far up in the order of operations on the last slide, right? You check all the nots, then you assess the ands, then you assess the ors. That's the order of operations for logical operators. So because not is so far up, it tends to connect, it tends to glue to one thing really quickly. And if you want it to modify this greater than or equal to statement expression, you need to put the greater than or equal to expression in parentheses, so that happens first. If I didn't have the parentheses, the not would have changed the x, and then it would do greater than or equal to, which is not what we wanted. So frequently for not, you've got to put the next thing in parentheses because of the order of operations. Okay, maybe document that for the next lab, because that becomes key at one point. Okay, so here's some ways that you can use logical operators pretty commonly. One thing that you commonly want to do is check numeric ranges. See if a number is in an acceptable range or not. So you could use logical and to see if a value does fall inside a particular interval range. So like normally, legitimate grade scores are between 0 and 100. So you could write if 0 is lesser than or equal to the grade, and the grade is less than or equal to 100, then you have a legitimate grade, and you can go and process it or turn it into a letter grade or something like that. Right? So legitimately, somewhere between 0 and 100. You know, you turn that around the other way, you could use logical OR to see if a value is outside an interval range and not valid. So you might see something like if the grade is less than 0, which is bad because it shouldn't be negative, or 100 is less than your grade, which is bad because the grade really shouldn't be 100, shouldn't be above 100, then you've got a bad grade, and then you can probably throw up an error message. Would be smart. So you could use it that way. Now, little cautionary note, what you cannot do in C++ is you cannot use mathematical chain notation. So this here, what I've written is mathematics, it's not C++. In a math class, you'll commonly write something like 0 is lesser than or equal to your grade, which is lesser than or equal to 100, which is really saying the same thing as the top part of this slide. Legitimate math, and it totally means what we wrote at the top. It means 0 is lesser than or equal to grade, and grade is lesser than or equal to 100. So you might see that in a math class, and it's kind of a nice shorthand, but you cannot use that in C++. Maybe someday. I don't know. You know, they're constantly expanding the language. Maybe someday they'll permit that, but to date, that is not permissible. You know, it'll compile it'll do something else than you expect, and you'll have a logic error, and it'll be very confusing because it doesn't, you can write that, but it won't do what you expect. Okay, so to kind of expand this, in our future programs, as we get user input, we are going to want to start doing input validation on the user input. What does that mean? That means checking the user input to determine whether it's acceptable or not. If not, you should throw up an error message and skip problematic processing blocks that would only work, on proper data. So as you when you detect that the input is improper, you throw up an error message, and this is kind of an important piece of text right here. You should display an error message that is clear, is specific, is immediate, and tells the user how to fix the problem. Okay, so I always look for that very, very carefully on my user interfaces for assignments that students give me. Are the error messages clear and specific to the problem, and immediately they happen right away, and they tell the user how to fix the problem is what we want. If you don't do that, you're going to have vague, confusing, unclear, late error messages, and your users are going to be very frustrated and not want to use your program anymore. So places where you'd want to do this, common test perform, is the input reasonable? Like if I ask for your age and you type in 1,000, that shouldn't happen. That's not reasonable. Don't deal with that. If I have a menu of which choice do you want, A, B, C, or D, and they type in Q, right? That we can't handle that. That's not on the menu. A numerical range, like that grade example, really ought to be between 0 and 100. If you're about to have a statement that does division, right? Remember, you cannot divide by 0. That's impossible. The program will be terminated with a divide by 0 error because the CPU just can't handle that. So you might have, validate a divisor to make sure that it's not 0. Otherwise, throw up the error message. For what it's worth, like in our class, right, I'm not asking you to invent this on your own. The assignments in the Gaddis textbook, starting now, will generally have like a little italicized note at the bottom. It says input validation. Make sure that the ages, are not negative and they're less than 200 or something like that, right? And say make sure that the prices are all positive numbers. Okay, so in this class, you'll read the assignments very carefully, or maybe the test questions, and only do exactly the input validation that's being stated there. We're not asking you to invent or design it on your own. Just program it. So here's an example of that. So here's program 419, and we've seen in the past a program that takes numbers and turns them into letter grades in a course. So this is very similar. We're just going to expand this a little bit with proper input validation. So the point here is this test scoring program does not accept test scores that are less than 0 or greater than 100, which makes sense. So kind of like we've seen before, we have some constants for the letter category cutoffs, but then we also have constants for min score, which is 0, and max score, which is 0. And then a variable for the input, and the prompt to the user, and you send in a test score. We've seen this before. And again, the interesting thing is on the next slide, what do we do with that? Okay, so here on line 24, and you can see on that comment, we're validating the input, right? So first of all, there's an if statement that says if the test score is greater than or equal to the min score, which is 0, and the test score is less than or equal to the max score, which is 100, then you've got a legitimate test score, and you can go into this block here, right, starting at line 26, and actually turn that into a letter grade. Okay, and that's code we've seen before with a big if, else if chain to determine the letter grade from a number. So you can do that. But if line 24 comes back false, right, where does the control flow go? Well, hopefully there is. So it goes into this else down here, right? You just jump all the way into that else statement. You'll be on line 40, right? And this is what happens if there's an invalid score being entered. And then it's going to print out that is an invalid score. Run the program again and enter a value in the range of 0 through 100. Okay, and then it goes on with the rest of the program, which is just this return statement, and the program ends. Now, of course, if you do have a valid test score, you get into this if statement, and then you skip that else and you don't see that error message. right? If something happens there, you just jump down to line 46 and you'd never see the line 38 block. But if you have an invalid score, you land in this else block and you get this. I want to emphasize that that error message satisfies the criteria for a good error message. Again, I did not write this, but I agree with this, that the error message is clear and specific and immediate and tells the user how to fix the problem. So it's clear that is an invalid score, right? It says very clearly what's happening. It's not like bad number. That wouldn't be clear. Very, very specific. This is an invalid score. It's specific, right? Specifically talking about the invalid score. Very, very clear like that. It happens immediately. So if a user is running this program, I'm just going to go back for a second, right? As soon as they hit enter on entering that test score, right, it immediately checks for the validity. It's the very next thing the program does. And if it fails, you immediately jump down to line 40, 41. You get that error message right now. You're not waiting for the user to add additional data. You're not asking, okay, and now what's your name? And now what's your phone number? And now what's your address? And then later on saying, oh, remember that test score you started with? That's invalid, and we're going to throw out all your data, right? That would really frustrate a user. You check the validity immediately right after the SYN statement and throw up an error message right then. And this error message also tells the user exactly how to fix the problem. They're going to have to run the program again and enter a value in the range of 0 through 100. Okay, so that's what you want it for, a proper error message, and you don't want it unclear or ambiguous, like bad number, and then just like, oh, and then another SYN statement, and the user doesn't know what to do about it. So that's a really good example as far as a proper error message. Now, I would like to test this program 419 with our first input validation. So here it is out of the program archive. I'm going to compile it. Great. I'm going to, just to get some extra space here, I'm going to close the compile log. So again, set up some constants, get a score from the user, and here's the interesting part here. So input validation happening on line 24. If it's a good quality score, between 0 and 100, we're going to go into this if block and actually report in a letter. Otherwise, the error handling down here in the else block. Okay, you got nested if else's inside other ifs. So I want to test it a couple times. What if the person has a grade of 82? Okay, the grade is B. Great. Okay, so that looks correct to me. What if the person unfortunately has like a 45? Okay, well, unfortunately, the grade is F. So in that case, at least it's between 0 and 100, so it's a legitimate score. I mean, that happens. Get into this if block here, right? And it's not above the A threshold. It's not above the B threshold. This is false. This is false. And so you wound up in this trailing else statement for the other stuff, which in this case would be F. But I also want to test this error message, right? If it's a totally invalid score, that shouldn't even happen. So if I type in 120, okay, it says that is an invalid score. Run the program again and enter a value in the range of 0 through 100. So that is that error message there, right? And this program is working correctly. That is an invalid score, and it gave me an error message, and I'm going to emphasize this again. It's clear, and it's specific, and it's immediate, and it tells the user how to fix the problem, right? I'm just going to go through that one more time about the immediacy part, right? So here's this. Type in 100. I'll type in, maybe negative 50, okay? Enter, right? As soon as I hit enter, the error message comes up. It's not waiting around. It's not waiting for additional input. It's not, 5 minutes later saying, oh, that thing over there, that was incorrect, right? You want, as soon as the SYN statement happens, right, the very next thing should be the input validation decision, right? And then immediately it's going to jump you into the error message right then. So clear, specific, immediate, tells the user how to fix the problem. That's a very good example of an error message. Now, one thing I will say is don't get too attached to this particular example of input validation, because the problem here is that if the user does type in a bad value, and I'll just do it one more time, like 150, okay, well, the program exits, right? I get the error message, but then the program's over. So in the next chapter, there will actually be a much better way of accomplishing this. that asks the user to correct the problem, right? The program is still running and says, here's a second chance. Please enter valid data before we go on. And if they still don't get it right, ask them a third time, ask them a fourth time. So that's actually a better way of doing this. When we get to the next chapter, that's what you want to do for input validation going on. You really don't want your program to just die as soon as there's one bad piece of input. So honestly, using an if for input validation is not the best strategy. And we'll get away from that in the next chapter. But this is a good, starting idea of, making a decision about whether something's valid or not. It's an okay starting point. It will be better, and in the future, we will not want to use an if for this, but it's an okay to start with. Okay, now so far, right, we've been comparing numbers for our Booleans with our relational expressions. Now, we want to expand to some other options, and among the other options are you can compare characters, right? Letters and symbols and punctuation. How does that work? Well, remember, everything's a number is how that works. So you can throw down relational operators like lesser or greater or equal to, and what the computer is going to do is it's going to compare those characters using their ASCII values. So we should dig into this. We've talked about ASCII values in the past, that characters are really stored as numbers. So I think now for the first time, I actually want to look at the appendix in the book and just kind of get a feel for the layout of ASCII. Let me pull that up here. So I'm looking at Appendix B of the Gaddis textbook. As of the 8th edition, it's Appendix B here for the ASCII character set. I think in later editions, they moved this up to Appendix A, which makes sense to me. And I'm just going to go to the second page. This actually covers 2 pages of material. I'm going to go to the second page where our letters start. Okay, and you see that we have 3 columns of numbers. We have the decimal number, which is our normal number. We have the hexadecimal number, which we talked about previously. We knew that hexadecimal was going to start to pop up once in a while. There's also octal here, which is base 8, which we didn't talk about, but the powers go 1 times 8 times 8 times 8 for what it's worth. And then you actually have the character that you would see on screen from that stuff. So for what it's worth, number 65 is how they represent capital A in ASCII, right? And then number 66 is capital B, and number 67 is capital C. And fortunately, it's laid out in sequence, so it does go from A to B to C to D to E to F like that in order, fortunately. Now over here, you've got lowercase letters. Remember, it is case sensitive, and you've got a different value for uppercase versus lowercase. So decimal number 97 represents lowercase a, and then 98 is lowercase b, and 99 c, and so on and so forth. Okay, so you might, on the one hand, you might say, why did they pick these numbers? Why was that weird that they picked 65 for capital A and 97 for lowercase a? But here's a situation where it makes a tiny little bit more sense if you look at the hexadecimal. Now remember, we could have put binary here, but the whole point is that binary is just too long and complicated. So we use hexadecimal as shorthand for that. So look at this. Notice that the capital letters start in the hexadecimal 40s, starting with number 1 for the capital A. So 40 and 1 is the A, 40 and 2 is the B, 40 and 3 is the C. So in hexadecimal, it does kind of start at something with 1 in it. Huh? And then you look at the lowercase character A, and look at this again. The lowercase stuff all starts in hexadecimal 60s, starting with number 1 for the A, right? And then 60 and 2 for the B, and 60 and 3 for the C. Right? So it actually makes a little bit more sense looking at the hexadecimal. That's why it was set up that way, looking at the hexadecimal, not actually the decimal, which is how programmers think. Now, if I go back to the first page, right, here is where you have punctuation. The exclamation mark is decimal 33, right? A hashtag is decimal 35 for what it's worth. I'm not asking you to memorize this stuff. It was important. Someday you could look it up. The digits, right? You need ASCII values for what the digits look like. And digit 0, that's not number 0, that's actually number 48, right? And then the digit for 1, if you want to see the symbol for 1, you have to use ASCII number 49, and so on and so forth. So you want to be careful that the character 0 is not the same as the number 0. Two different things, and some more punctuation. And then over here, you actually have some special codes that just aren't visible. Like, let me see, there's the tab key, I guess is number 9. There's carriage return, which is actually the enter, right, is actually number 13. There's a code here for an audible bell, which is number 7. And then there actually is a character for null, which actually is the number 0. I think we've talked about that in the past because that's the symbol that C++ uses to indicate the end of a string, right? I say hello, I've got the capital HELLO, and then you have to have number 0, which is to say the null character, and that's how C++ knows you've got the end of a string. Okay, so don't need to memorize this, which is kind of interesting to see that. Notice that, the digits are laid out in order at least. The capital letters come first and are laid out in order. Then the lowercase letters were added later, so they have higher numbers, stuff like that. All right, so let's go back to our slideshow. So so back to comparing characters here. So we said that if you throw down relational operators between characters, the computer just treats them like numbers and compares using their ASCII values, for example. So if you compare capital A to capital B, say, is capital A lesser than capital B? Well, the ASCII value of A is 65, and the ASCII value of B is 66, so this actually comes back as true, right? From the computer perspective, it's just comparing these ASCII numbers. From the human perspective, this is saying, does A come before B in the alphabet? And that's how we can use that, right? Does A come before B in the dictionary? And the lesser than sign gives you the right answer to that. Or, you could compare digits, right? Is character 1 coming before character 2? Is character 1 less than character 2? Well, as we saw there, the ASCII value of 1 is really 49, and the ASCII value of 2 is really 50. That's really what's being compared. Is 49 less than 50? Yes, true. So, computer perspective, it's comparing 49 and 50. Human perspective, does 1 come before 2 in a phone book? Yes, it does, and this comes back as true. So this kind of, again, the computer's doing one thing, but it totally does the job that we want to see what comes before something else alphabetically. And you can compare punctuation and all that kind of stuff, and it just compares the ASCII. Now, one thing to be careful about there is we saw that lowercase letters have higher ASCII codes than uppercase letters. So if you compare lowercase a, that's actually greater than uppercase z. So be a little bit careful about that. So again, these things are case sensitive, and the lowercase letters are actually greater than come after the uppercase letters. So be careful about that. You can totally do that. And let's build on that. So here's program 420, which is kind of an interesting example here. This program demonstrates how characters can be compared with the relational operators. So you're going to have the user enter a character, right? Prompt them, enter a digit or letter, just anything on the keyboard you like. And, because we're not just using sin arrow here, because we also want to permit the user to enter spaces or tabs or enters, which the sin arrow just skips over. So in this case, you can see we're using this function called sin.get that will get one single character of any type whatsoever, including spaces and tabs and stuff. You put that into CH, and then you have an if-else-if block using logical operators. So if the character is greater than or equal to the 0 digit, what was that, like 48, whatever that was, and the character is lesser than or equal to the 9 digit, which would have to be 57, I think, then it's one of the digits, right? It's in that range in the ASCII table of the 0, 1, 2, 3, 5, 6, 7, 8, 9 range. It's got to be a digit. So this program will print out, you entered one of the digits, right? Maybe it's 1 or 2 or 5 or 7, one of those things. Now, if it's not that, you land on line 17 and you check in, is the character greater than or equal to capital A, which I think was 65, okay, and the character is lesser than or equal to capital Z, which is technically ASCII what, 81? No, 91, something like that. And if it's in that range, then it's somewhere in the capital letter range, right? And you can print out, you entered an uppercase letter, maybe capital G, maybe capital T, right? If that doesn't happen, then you land on line 19 and it checks in, are you in the lowercase letter range, right? If the character is greater than or equal to lowercase a, but it's coming before lowercase z, right? It's in that range of A to Z lowercase in ASCII, and we can print out you entered a lowercase letter, right? Otherwise, if it's not any of those things, we have our trailing else, and it says, well, that's something else. It's not a digit or a letter. Maybe a space, maybe a tab, maybe an enter. I don't know, one of those things. So you might want to try this on your own and confirm that this actually works for anything that you type on the keyboard. Will actually get reported properly. And we're knowing a little bit about how characters are compared because we know about the ASCII table, and we are using logical operators like AND here to determine a range of values. For us, as humans, are you between capital A and capital Z? But for the computer, are you between ASCII number 65 and ASCII number 91 or whatever it is? So kind of neat. So now let's expand on that and think about comparing whole string objects. Remember, string is a bunch of characters. That example was just comparing one character at a time. But similarly, more or less works the same way. Like characters, strings are compared sequentially using their ASCII values. So once again, you can just make two strings. Okay, so here I've made string name1, which is holding Mary, and a string called name2, which is holding Mark. And you can still compare these with just throwing down relational operators. Okay, so this is all legitimate C++. You can check and see if name1 is greater than name2, which is really going to determine, does name1 come after name2 in the dictionary? Right? You can check, is name1 lesser than or equal to name2? Does it come before it? You can check, is name1 not equal to name2, different than it? Right? So any of those things are possible. Now, so this is built in automatically to our C++ as long as you're using a string object. There was some other programmer that did quite a lot of work for this to just happen magically for us. Now that that's happened, we can just use a greater than symbol to determine whether one string comes after another. Now, if you dig into the details about what's happening when that occurs, right, what it would do is it's really going to compare one character at a time. Of course, it does it so quickly, it looks like it's all one thing. But if you're comparing these two things, it would say, okay, I'm going to compare the first letters, capital N to capital M. Are they different? No, they're not. So I better go check some more characters. Okay, right at the moment, I don't know if there's any difference. Okay, lowercase a and lowercase a. Well, those are the same. I haven't spotted any difference yet. Right, and then it compares lowercase r to lowercase r, right, just one character at a time. Well, those are the same. I still haven't seen any difference. And then it compares lowercase y to lowercase k. Okay, here's a difference. And yeah, y is greater than k. Y comes after k in the alphabet. Now I have a difference, and the greater than symbol comes back and reports that as the difference. And this will actually come back as true. Right? The first difference that it found, the y character was actually greater than k. And so from the human perspective, yeah, Mary should come later in a dictionary than Mark. So really, it's just comparing for dictionary order when you get to use this. A lot of work happening under the hood that somebody else did, but from our perspective as C++ programmers, it's just telling you which one comes first in a dictionary. Nice. What do you think about the second one? Is name1 lesser than or equal to name2? Does name1 come before name2 in a dictionary? Or is it the same as it? Well, hopefully you agree that's false, right? If name1 is actually coming after name2, like we said in the first example, it can't be coming before it. So that would be false. And this third one, what is that? Is name1 not equal to name2? Well, that's actually true, right? I mean, they actually are different. So if you do need to compare strings, you can just use relational operators like anything else. Now, I will say this is a place that's different from other languages. It is not this simple in C. It is not this simple in Java to compare strings. You have to use a slightly more complicated function to get this job done. But in C++, they did, this is called overloading operators, make the lesser than, greater than, equal to symbols automatically compare strings. And for people coming from other programming languages, they're usually very bewildered that it's this simple, because this is actually not something it's quite so easy in other programming languages, but it is in C++. So win for C++. Okay, so at this point, you can basically compare anything, right? You can compare numbers with your relations, you can compare characters, you can compare whole strings, right? C++ is very flexible like that. And you can combine your decisions together with logical operators, not and or, particularly to determine whether something's in a legitimate numerical range. And you can use that for your input validation and a whole bunch of other stuff. So at this point, my students would get together in person and we do this lab 4.3 on logical operators. You know, it's a very short little program, but we are trying to use the logical operators correctly to make a couple decisions here about whether someone's ready to graduate in a particular case. You know, a registrar at a college system might have this programmed in the system to send out notifications, right, about getting ready to graduate pretty soon. So we want to make sure that that's working correctly. As we usually do, we're going to write a test script with several different conditions to consider, confirm the program's actually working correctly, make a couple modifications. So a very short program tends to be kind of challenging the first time you're using logical operators. You know, you have to look really, really carefully at what we said in the lecture videos in order to use them, I guess, for the first time here. So if that's challenging, that's not a bad thing, and hopefully it sticks in your memory. And that's what we ought to be doing. So when we come back next time, the next video is going to wrap up chapter 4. We've mostly been focused on if-else statements to make our decisions, but that's not the only possibility in C++. There's two other ways of making decisions. There's the switch statement, and there's also the conditional statement, or what some people call the ternary operator. So those will make our code a little bit shorter, sometimes easier to read in certain circumstances. We ought to know about those, be aware of those in other people's code, and that'll be next time. So I'll see you then.